Lecture 5 is the second of the pump system components discussion, where we began in Lecture 4 to talking about pumps. Now we're going to move into Lecture 5 here, and we're going to talk about pump characteristics and looking at the pump curves, trying to understand those. And then we're going to go through this concept of net positive suction head available. And we'll talk about net positive suction head required. And this is somewhat of a difficult concept for students to understand at times. So you'll need to pay particular attention to this and really work the homework problems. This all centers around this concept of cavitation. So let's revisit our terms. We've got a pump head characteristic curve, which is that relationship that's developed for a pump. It's supplied to you by the pump manufacturer. It is the relationship of the pump head versus the Q, and it looks like this. We've got a modified pump head characteristic curve, which is when you've got two or more pumps together, and we'll talk a little bit about that. In this particular course, I'm not going to give you any kind of problems with multiple pumps. If I can get you to understand how to design a single pump, I'm going to feel real good about that. The shutoff head, which is that value, if you notice up here, this is all the flow rates possible for this pump on this pump head characteristic curve. The shutoff head is going to be that value that is right at the amount of head right as the discharge goes to zero. You notice here that as the discharge increases, the amount of head that the pump can impart into the flow decreases. So the shutoff head is that head output at zero discharge. Then the normal discharger head is the discharge when the pump is operated at the most efficient level. So if you have some sort of efficiency curve here, this will be maximum efficiency. You maybe have efficiency plotted on this axis, and so this is this curve for that. The maximum efficiency point would be right there. So that'd be that sweet spot. That's going to be the normal discharge head. And then that's also known as the rated capacity. So these two terms are synonymous. The brake horsepower is going to be the amount of power required by the pump to get the required discharge. That's often called the BHP. That's the brake horsepower. And then the pump efficiency, you've already mentioned that. That's this value of nu, which is the power imparted to the flow by the pump, divided by power required by the pump. And we'll talk more about that. And then the best efficiency point, again, is this location right here where this the normal discharge occurs. That's the highest efficiency that the pump can attain. And then the pump operating point is the point where the pump curve and the system curve intersect. We haven't talked about system curves yet, but we're going to look at a system, and you're going to compute the system curve. And those two things, one is the pump head capacity curve, the other is the system curve. And where the intersection of those two occur, that's what's going to be this pump operating point. And we're going to get to that in subsequent lectures. So again, this is the graph here of a pump head versus the flow. This is the pump head characteristic curve here in red. And then you've got your power curve, you got an efficiency curve, you got the net positive suction head required curve. These are some things you haven't talked about. We've talked about efficiency, and we've talked about the pump head curve. And the power required curve is also often supplied by the pump manufacturer. And then this thing called the net positive suction head required, that's going to get at this issue of cavitation. You're going to have a certain net positive suction head required. That's on the inflow side of the pump. You've got to keep that at that level or above in order to keep away from cavitation, which we'll talk about later in this lecture. If we're going to calculate this brake horsepower, the brake horsepower is going to be computed as such that we've got the unit weight of the fluid, and if this is British gravitational units, that's usually 62.4 pounds per cubic foot. And then we've got the flow rate in cubic feet per second. We've got the head of the pump, right? So this is the flow rates put through. Then this is the efficiency. And we also sometimes abbreviate that as nu. Here we've got it as E. And then this 550 is in order to put this brake horsepower from foot-pounds per second to the units of actual horsepower. So we've got this brake horsepower, which is, I could express it in units of foot-pounds per second, but if I want to put it in terms of true horsepower, I just divide it by 550, and that's just a conversion term. And you'll notice down here when I'm using SI units, I don't have the 550 because, again, we're talking in kilowatts here, and so it's still this whole concept of the unit weight of the fluid times the flow rate times the head that's imparted. That is the power that the pump puts into the fluid, and then the efficiency is how good the pump is at converting the brake horsepower to the power to the fluid. And if I swap these, so if I typically it would be gamma QH over the brake horsepower, but if I flop those around, I can solve for BHP. Okay, so know these definitions. You may have a problem in the quiz that talks about that. Just know how to compute it. This is an example of a pump manufacturer's curve. You've got capacity flow here on the X. You've got the head here on the Y-axis, and you notice here that you've got these various dimensions. These are the diameter of the pump. You can notice 27-inch pump diameter. That's a pretty big pump, and you can see here that each pump diameter has its own curve. This is a pump head curve for a 27-inch pump. Here's one for a 28-inch pump. Here's one for the 30-inch pump, 32, and 33-inch pump. And you'll notice these are in thousands of gallons per minute. So this is 9,000 gallons per minute. And you can look and say, okay, for the 27-inch pump, if we were pushing, let's say 7,000 gallons per minute, I would be imparting a head of about 158 or so feet of head. Now, the other thing is, you'll notice you've got the efficiency curves here. So this is 85% efficiency. This is 84 on down. The higher efficiencies are basically kind of centered here in the middle, and you move away from that as you get away. You're never going to have a pump that's 100% efficient. It's just not possible. And then the last thing to mention on this particular graph is the brake horsepower. So if I have this, back to this example of operating at 7,000 gallons per minute, 152 feet of head, or 158 feet of head or so, I'm going to estimate that brake horsepower somewhere between 300 and 400 horse would be what would be required to get from the utility to run that pump. All right, this is another pump head capacity curve that's put out by Gould Pumps, and I just show it's just a slightly bit different. You still have the pump characteristic curves. Here we start with a 12-inch, goes all the way up to a 17.5 diameter pump. You've got those pump curves there, and then you've got your efficiency curves here with these straighter lines, and then superimposed on that is a net positive suction head required. And you can see these got values here of 7 feet, here's 10 feet, here's 16 feet. And then down here, we've got our values of the kilowatts required. Sort of the brake horsepower is shown here in this graph. And here's the kilowatts down over here on the right. And again, these are plotted in both feet and in meters, and you've got both meters cubed per hour and gallons per minute on this pump curve. This is just an illustration, showing if I had the same pump but it was variable speed, what it would look like. So here's operating at 500 revolutions per minute all the way up to 1,200 revolutions per minute. This is not multiple pumps here like you've had on the previous curve. This is just one pump that has a variable speed operational capability. If I had multiple pumps, and this is one thing that I've told you I'm not going to make you design for multiple pumps, but I am going to make you understand this concept. And this is the concept of whether I've got a pump in parallel or pumps in series. And so if I've got pumps in series, I'm not adding any additional flow, I'm just adding head. If I've got pumps in parallel, I am not adding any additional head, but I'm adding additional flow. And if I were to give you these two particular graphs, I would expect you to be able to reason out whether it was a pump in parallel or a pump in series. You can see these modified curves here. So if I only had one pump operating, this is what I would have for a pump head curve. And then if I've got two in this particular configuration, I've got the modified curve of both pumps acting together looks like that. So I ask you, what is this? Is this a pump in parallel or is this two pumps in series? And I'm going to say that this is a pump in parallel because I'm not adding, if you look at the shutoff head here, even with that second pump, I'm not adding any additional flow. I'm just adding additional, I'm not adding additional head. I'm actually adding additional flow. If this was in series, I would expect that the modified curve would be drawn up here, much like it is over here. So you can see here, I'm just adding flow rate to this. As I add this second pump comes online, I'm just increasing the flow. So that's a key tip-off that it's a pump in parallel. A pump in series, I'm not really adding flow for each additional. So if I'm at this flow rate, I'm not really adding flow, I'm just adding head to that same, once I kick that second pump on. So this is a pump in series, pumps in series. These are pumps in parallel. So make sure you understand that. This operating ranges, you know, our goal is to select a pump that's going to be operating at the maximum efficiency. But you, as you move away from that, the pump will wear. It might not operate as efficiently, so you're going to decrease it. So we want to try to stay in that maximum efficiency range if we can, but we almost never operate solely in that BEP. And so you've got to establish in your design what your minimal acceptable efficiency is, and you can set the upper and lower limits on that. And if you see, typically what we are is we're operating in a range of, you know, and so if you're acceptable between 60 and 120% of the best efficiency point, so that's basically if this is where you're at for your best efficiency is right here, this is the sweet spot. If you're willing to accept a range of that, this is operating around that range. And so it's just a good concept to keep in mind that you've got an envelope that you're operating your pumps in. So I want to kind of now get onto this concept of net positive suction head, what it is, and it really revolves around this concept of cavitation. Cavitation is defined as when water changes from a fluid to a gas. And so you can, if you put water on the stove and you boil it, you know, you turn the heat up and it's going to boil. And if it's at sea level, that's about 212 degrees Fahrenheit. It's changing from a liquid to a gas in that, but we're adding temperature to it. And that is not exactly the same thing because cavitation, we're not necessarily increasing the temperature. What we're doing is we're lowering the pressure. As the pressure lowers, then if it gets down to near the vapor, what we call the vaporization pressure, that fluid will create air bubbles. And as pumps are really bad in this sense, as the impeller is spinning, you get areas of extremely low pressure. And if those pressures go below what we call the pressure vaporization or vapor pressure of the water, then that water will instantly turn into air or vapor. And then as soon as the pressure raises a little bit, that air bubble collapses. That's called cavitation. And I've got a couple of videos that you can watch and understand about cavitation maybe a little more. And so this slide talks about kind of the dynamics in terms of the pressures and the velocities. These collapse and vapor cavities are quite damaging to the pumps. They'll pit the pump. When you get cavitation occurring, it will wear out the bearings very quickly. When you have these cavitations collapsing, the speeds of these jet velocities of the cavitation of the bubble imploding has large pressures and large velocities, and so it's kind of equivalent to a jet striking a solid wall. It's very very damaging to the pump impeller. So what we want to do is we want to define the net positive suction head available on a problem. You're going to solve for this. Now, I told you that the pump manufacturer will give us a net positive suction head required. What we want to do is we want to keep our net positive suction head available greater than that net positive suction head required. And the way we're going to do that is we're going to calculate the net positive suction head available is the following form of the equation. We're going to take the total energy at point A, which is at the eye of the pump, upstream of the pump, on the upstream side of the pump, and we're going to take that. This is what we're going to call H sub A, the total energy at that location. So you've got the potential energy, you've got the pressure potential energy, you've got, notice that we're going to use absolute pressure here because these pressures can go below zero. We can actually get a negative pressure in terms of gauge pressure, so that's why we use absolute pressure. Just to remind you, P absolute is equal to P gauge plus P atmosphere. That's from fluid mechanics. And so that's what we're talking about here. This turns this gauge pressure, which is PA over gamma, once we add it to the atmospheric pressure, that becomes the absolute pressure. And so in working these problems, whether they be a pipe flow problem or whatever, the only time I actually use absolute pressure is when I'm working net positive suction head available problems, because I don't want I don't want to be dealing with negative pressures, and that's why we do that. And so we're going to take that HA, and then we're going to subtract off the elevation ZA, which again, if I've got a datum here, this is Z is equal to 0. This is going to be my value of ZA, okay, if that's my datum. And so notice it shows up here and here, and I always do this. Some textbooks, you'll see them just eliminate the ZA altogether, but I like to keep it together because I think it really emphasizes what we're talking about here, and it results in less mistakes. So I've got this subtraction of this combination of the energy, of the location of the eye of the pump, plus this is the vapor pressure. PV is equal to the vapor pressure of the fluid. And you look that up in a textbook. And and I will give you a quiz problem on this. I'm going to give you the vapor pressure, so you won't have to be looking it up. So again, as I said, some textbooks will simplify it, get rid of the ZA, and they'll show it in that form right there. The key is, don't be lured into, even in Chin's chapter 2, which I've given you, he will give you kind of a shortcut equation for this, which will be based on a reservoir problem. And it's got the delta Z in it and some other things. Don't be lured into that. Always go back to first principles and working one of these problems, first stating this definition. That way you end up working the problem correctly. And so what we want to do, as I've mentioned, is we want to keep that net positive suction head available. So when we design a pump, we've got this pump head characteristic curve. We haven't talked about it yet, but you're going to develop a system curve. And the intersection points would be where, if I selected this pump, this would be where it would operate in terms of a Q and an HP. But we would want to know not only that, what is the net positive suction head available for this configuration? Because we're going to be designing this pump, and we're going to, not only do we have to worry about what flow rate and head it imparts, but we also have to make sure that it stays above this required net positive suction head. This will result in no cavitation if we meet that design requirement. And so as we go through this, We've got this curve here, or we'll get the graphic, which you've seen before. And I have this as my system. This is the water surface elevation of this reservoir. And I've got my pump here. And this is my point A of this pump. Okay, so I've got point A there. And I'm going to basically write an energy equation from location 1 to point A. And so I write my energy equation. If you notice here, I've got, I'm going to assume that the velocity at section 1 is approximately equal to 0 because I got this reservoir. I've got the P1 over gamma is equal to 0 because it's vented to the atmosphere. But I do have the atmospheric pressure at that location. And for lack of anything else, if I never tell you atmospheric pressure, just assume 47.1 psi. 14.7 psi, sorry about that, 14.7 psi, and then you'd have to convert that to pounds per square foot, so you multiply it by 144 to get it into pounds per square foot, and so you'd have that, and so now the ZS would be, if this is my datum here, this is my datum equal to 0 right there, so I've got the value of ZS added, and then I'm writing it to this point right above the upstream end of the pump. And so I've got what ZA, which is the elevation of the pump, the pressure at that location, that's the gauge pressure, the atmospheric pressure is added in, and the velocity head at that location. I'm going to wall this off, and I'm not going to touch this. I'm not going to plug anything in. I'm going to call that H sub A. And then I've got to factor in the losses, right, that occur between location 1 and 2. So I've got entrance losses as the water flows into this pipe entrance. I've got the friction losses, and then I've got the minor losses. That's like the gate valves and any kind of thing that would cause a localized, like maybe I've got a bend in the pipe or whatever. And so I'd have to consider those. Now, the next thing I do, so I've got that energy equation, or that, the energy relation between some point where I know a lot of information to the eye of the pump. The next thing I know is write the definition of net positive suction head available. And what I'm doing there is I'm going to say that's essentially HA minus this business here, this vapor pressure, which I talked about on the previous slide. Now, again, I'm going to solve then equation 1 for HA and plug it into this definition. That's what's going to help me actually compute the net positive suction head available. I'm going to rearrange that equation 1 then and isolate in terms of this HA, and then I'm going to plug that back into equation 2 and to calculate this, because this end of things with the PV over gamma, that's a textbook value. I looked that up. That's a property of the fluid. And then so we're running this through. Here's just sort of plugging that back in, and that's, you know, sort of how you calculate that net positive suction head available. And again, we're reminding you that you've got to make it greater than the net positive suction head required in order to prevent cavitation. This will become clear when I work an example problem in a second.